will proceed in circulation density, that is curling factor in calculus. We have come too far as curling is concerned. So what is curling, and what is the scenario that we are seeing that is different from any vector? We have vector field. We have vector field, and that's how it is different. We have vector field, and that's how it's different. Otherwise, when we had a vector, things were simple. If we had a vector, things were simple. What is the work done? Consider not a vector. Consider not a vector. What is work done? Force into displacement is work done. I am applying force and displacement is happening. Whatever the displacement happened, A to B, displacement is B minus A into force. That is the work done, that is in joule. So mass into acceleration is the force. I believe that is the Newton, into distance is the joule, that is the work done. What is the work done? What is the work done when force is like this? Then I have to move same distance A to B, I have to apply more force. Means force direction matters. If I talk in numeric way, force into displacement force into displacement is work done, then it is considered that it is a special case of force when force is in direction of displacement, but force can be in different direction. Now what is force into displacement? This, if this is force, then what is the force essence, force effectiveness along the displacement direction? F cos theta. If this angle is theta, then F cos theta, then what is the effect of this force along the displacement is F cos theta, then pushing it. So now if I apply force, then net force that is along the displacement is less. F cos theta maximum is 1. So when theta is 0, then only full force is applied in the direction of displacement. Otherwise, F cos theta. Or if I take displacement also as a vector, then F force, F vector dot displacement vector is the net work done. Wow! Means we have really done some kind of development where we are talking about not only about the magnitude of the displacement and magnitude of force, direction of the displacement and direction of the force, everything we are talking now. We are happy. Force vector dot displacement vector is the work done. Okay, now okay, now force is like this. When displacement made something, then force become like this. Then displacement was something, then force become like this. Then displacement was something, then force came down. For as per the displacement, force is changing its direction. Now, instead of displacement being on a straight line, displacement is circular. Now it is moving like this. Very nice. After some time, it started moving like this. After some time, it is moving in a circular direction. Oh my God! Force is varying. Point to point force direction is varying, and its magnitude is also varying. Point to point displacement is also varying. Now we have entered into algebraic vector, where the component of vector is algebra. Independent algebra means a function over independent components x, y, z, whatever it is. So now we have entered, now the force vector has turned into force vector field. Now the displacement vector has turned into a displacement vector field. What is the work done? Every moment force is like this. Here force is like this. Here force is like this. Here force is like this. Every moment force is changing. Displacement is also changing. It's not a straight line. If that is the case, then every moment if I take a small distance where I consider distance as a straight line, then at that moment the work done is is vector force vector dot displacement vector. But if I want everything in algebra all through, not adding each moment, then it will come as calculus, and it is capital F, that is the force field dot d r vector, where r is the line, dr vector, where r is the line. I believe it makes sense, where r is the line. So capital F, capital F, capital F, capital F, that is a vector field, capital F, that is the vector field, capital F, that is the force field. Now force field converted into vector field, algebraic vector. Earlier the force field was 2i plus 3j. Now it is x plus yi plus x plus sine yj. Now each component is algebraic equation. If each component is algebraic equation, now it is a vector field where if I keep changing x comma y, the net vector will keep changing. Okay. Similarly, the displacement vector, earlier it was a straight line like I vector, x-axis. Now it is xi plus yj, and if it is circular, then it is xi plus a square root of a square minus x square j. That is the line vector. So capital F, vector field capital F dot dr vector, capital F dot dr vector, where r is the line vector. So if I go with the dot product of two vector field, then it gives me the work done if capital F is force vector field. So capital F force vector field dot, not displacement vector r vector, dr vector, where d is calculus. So dr vector. So r vector here is circular line, and force vector is whatever the force vector is. So if force vector is a vector field and then we are integrating along a line, this is also called line integral. For any vector field, velocity vector, magnetic field vector, electromagnetic vector, any vector field, dot dr vector, where r is the line, any vector field dot dr vector is the line integral. If vector field is force, then it is also work done. Otherwise, it is pure line integral. Pure line integral. So force field, force field dot line vector, force vector field dot line vector field, capital F dot dr vector is the line integration, line integral. If capital F is force vector field, then it is work done. Okay, now we are in discussion for the curling, when it would produce curl. Now it would produce curling. When it would produce curling, consider that this is x-axis. Consider this is x-axis. This is point A and this is point B. A, B. This is B to C. We have talked about it. A to B and B to C. C to D, D to A. This is a rectangle. Rectangle. Now, there is a some vector field capital F. Okay. What is the line integral of vector field along the circular, around a rectangle. Okay, mind it, I'm not talking about the surface, only line. Line here, line here, line here, line here. There is a rectangular line. What is the line integral of a vector field capital F along the rectangular line? That is capital F dot dr vector from A to A, that is A to B plus B to C plus C to D plus D to A back. That is the line integral of vector field capital F along the rectangular line. If that is the case, then what it is? We are talking about curling. What would generate curling? What would generate curling? Now consider the vector field. Repeatedly I am giving this example. Consider the vector field is x plus yi plus 0 j. There is no component of j in the vector field. So vector field is along x axis. Okay, x plus y I. Now what is line integral from A to B? That is x plus y dx. Means the line vector here is xi plus yj. If I take any point on x axis, that is x comma y, then the vector is, if it is origin, any point is x comma y, then this vector is x minus 0 I plus y minus 0 j. That is the equation of position vector. Now capital F dot dr vector is the line integral. Now capital F dot dr vector. Now r vector is xi plus yj, d the dx plus dy. But y I have taken as 0. Not only that, there is no j direction at all. Actually, when we deduce a kind of vector, then we subtract one point to other point to get the vector. If it is 0 0 0 0, then this point is x comma y, where y is 0. So this vector is nothing but x minus 0 0 minus 0. So it is xi. This vector is xi along x axis. So dr vector is dxi. Now here capital F is x plus y I have taken. Now net integral is x plus y dx. X plus y dx is the net line integral. Line integral along this is 0, because this is completely in y direction, where I have vector field completely in x direction. So dot product will be 0. No line integral along this direction, no line integral along this direction. If that is the case, then line integral will happen along this direction and line integral will happen from C to D. What is line integral here? Line integral is x plus y dx, where y equal to 0. X dx. X dx is the line integral. What is line integral here? That is x plus y dx. Y is 10. If I take 10, then it is x plus 10 dx. So x plus 10 dx, here the line integral is a to b. Line integral is a to b. This is 0. Then line integral from c to d. C has higher x value, d has lower x value. If I integrate c to d, x plus 10 dx, the result will come as negative, or result will come as positive if I take this direction as line integral. So whatever, if that is the case, then net line integral is from here to here, then here to here 0, or then here to here negative. Let's take negative one. If I take negative, then here to here 0. If that is the case, then line integral will be this plus this. This being negative, so net line integral will be this minus this. Here it is x dx, here x plus 10 dx. X plus 10 dx. So x gone. Now it is minus 10x. Minus 10 dx integration is minus 10 x from point from point C to D. If it is from point C to D and it is minus 10x, then D to C will be 10x. Means net line integral is along this direction only. But it is nullifying this. Please concentrate here. So here I have line integral from A to B, that is capital F dot dr vector. Now r vector is x-axis and capital F is x plus y I plus 0j. Y is 0. Y is 0. So x I dxi means x dx. Here, here it is x plus 10 dx. So x dx plus 10 dx. Net will be, I have to add these two. But it is C to D. C is higher, D is lower in x-axis. It will result in negative. So it is minus. Okay, if I consider D as x as origin, then C to D, D being 0, completely 0, and then D, then C, whatever it comes, come as negative. So minus x dx, that will be minus x square by 2, minus 10 dx minus 10x, plus x square by 2. Net will be minus 10x. Consider C to D is unit length, A to B is unit length, then it is minus 10x. Minus 10x in this direction, that is the line integral. If I consider in this direction, it is 10x. So at the end, the line integral of this rectangle is 10x in this direction. If it is like this, the net line integral is not 0 from point A to A. This is A. This is A. From A to B, B to C, C to D, D to A back. From A to A, net line integral is not 0. If it is not, because any integration, if I calculate A to A, any integration, if I calculate A to A, then it should be 0. But it is not 0. If it is not 0, it will produce curling as per the mathematics. But in real scenario, just think that if there is a rectangle, if there is a physical rectangle like this, and this side there is a force that is pushing this direction, and here also there is a force that is pushing in this direction. If these two forces are same, then the rectangle will move like this, but it will not rotate. Mind it. If vector field is in this direction, and there is a rectangle, if there is a rectangle and this side of the rectangle, the line integral is 0, this side of rectangle line integral is 0, this side of rectangle line integral is there, this side of rectangle line integral is there. If both line integral are same, if they both line integral are same, then net line integral from here to here to here to here to here back A to A is 0, whatever it is. But there is a positive line integral along this direction. There is a positive line integral along this direction. Means that the vector field, if it is in this direction, it will push the rectangle along the vector field, but it will not rotate it. But if the line integral here is less and line integral here is more, then it will place a torque here. Can you see it is more? Since it from here it is more, it will place a torque here. So it will move like this, but it will keep rotating also. This is called curling. What triggers curling? Curling triggers when the vector field what we have here and vector field what we have here in rectangle, they are different. If they are different, then it produces curl. If they are different, if something comes as different, then there is dy by dx. I mean, per unit change, how much is the difference? What is the change in the unit? Here, if I take this vector field here, if I take vector field here, then the difference is in y, because x is same from origin to one point, from origin to one point. X is same, Y is different. So this vector field capital F is changing if I change the Y. If this capital vector field is x plus y I plus 0j, then capital vector field capital F is f1I plus f2j. This proves that f1 is x plus y and f2 is 0. In that case, f1 is changing as we move along y direction. How much it is changing per unit change in y? df1 by dy. If there is df1 by dy, it will produce curl in this direction. Now consider a vector field that is 0i, 0i plus x plus sine yj, 0i plus x plus sine yj. If that is the case, then f1 is 0. Then line integral from here to here, f1 dx is 0. But whereas here line integral will be there. Again line integral 0. Again there will be a line integral, that is f2 dy. f2 dy. Line integral here f2 dy. Consider this is origin and equation of the f2 is x plus sine y. Then x is 0. Now here it is sine y dy. Here if I move 10, and then what is the x plus sine y dy, that is the line integral here. X is 10, 10 plus sine y dy. Now I am calculating line integral from here to here, here to here, here to here, here to here. So this side it is here to here, whereas this side it is here to here. So in y direction both are opposite to each other, mind it. So if I calculate line integral from here to here, from here to here, then it is positive. Top to bottom, lower to higher line integral will be positive. And then it is y, then it is x plus sine y dy. X is 10, 10 plus sine y dy. Whereas line integral from here to here, here to here, here to here, here to here. So line integral from this point to this point. So higher to lower. Line integral from higher to lower. Lower is 0. Means it will be negative. So it is sine y dy minus sine y dy. But it will be in this direction, downward direction. If I want upward direction, then it will be positive. Sine y dy, whatever it is. The net line integral is from here to here, 0. Here to here, 10y, 10 plus sine y dy. Here to here, 0. And here to here, minus sine y dy. If I add, it will become 10 dy. 10 dy is the line integral. Consider this and this, the difference is 1. 0 to 1. So it will be 10y is the line integral 10. So this proves that the line integral is again not 0 from a to a. If this point is a, and a to a line integral, that is a to b, b to c, c to d, d to a, where the vector field capital F, is 0i plus 10 plus sine y j. If this is the vector field, again the net integration from a to a is not 0. If it is not 0, then it will produce curl. It will try to rotate something if it comes in a vector field. What is the rotation? Now this side, the line integral is in this direction. This side, the line integral is in this direction. So the net line integral, what we see to rotate in terms of rotation, then this minus this, whatever comes, then it will try to rotate in this direction. If this one minus this one is same, if both are same, then it will push through. Our vector field is in this direction, 0i plus x plus sine y, where here the vector field is less because x is less 0. But as we move along, the x is gaining the quantity. If that is the case, then here it is 10 plus sine y, that is the vector field. Vector field is gaining strength if I move along x-axis. Now here the vector field power is more, here vector field power is less. Consider both are same. then if this is the vector field, if I place item here, it will try to push through like this. But if vector field is varying and it is increasing in this direction, then this side torque, if this is the item, this side torque is more than this side. So it will not only push through, it will try to rotate it also. Okay, we have taken both cases. One case where vector field is only along x-axis and it is varying as we move along y. Then the tendency to rotate the any item, that is df1 by dy. Now we have vector field only along this direction, and if I go from this side to this side, then vector field is growing. If that is the case, then vector field try to rotate an item which is placed like this, then like this. If that is the case, then what is tendency to rotate? That is F2 dF2 by dx. As if I move one unit along x-axis, then how much there is change in F2. If F2 is changing more, then here F2 is less, here F2 is very high because dF2 by dx is very high. If I make one unit of change along x-axis, how much is the power of F2 is growing, dF2 by dx. That decides that how much it will rotate it. If dF2 by dx is 0, then here the line integral is same, here line integral is same. It will push any item along y-axis, but it will not rotate. Here F2 is there, here F2 is there, but there is slight change. Then it will move slightly and it will go along. But if here F2 is there, here F2 is difference is very high, then it will rotate quickly and then it will go up. How much it will rotate? It depends upon if I change along x-axis, how much F2 is changing, dF2 by dx. Now we see that dF2 by dx make rectangle rotate like this, and dF1 by dy make rectangle rotate like this. Then again they are nullifying each other. What is tendency of any item to rotate like this if F1 and F2 both are there? Means equation is x plus yi plus x plus sine yj. X plus y in bracket I plus bracket x plus sine y bracket close j. If this is the vector field, then capital F1 is x plus y and capital F2 is x plus sine y. If that is the case, what is the tendency of any item to rotate by the vector field? That tendency is nothing but in this direction, means in df1 by dy. So df1 by dy minus df2 by dx means what is tendency to rotate in this direction minus then this one. What is tendency to rotate? If I subtract, then what is the tendency to rotate in this direction I'll get. Or if I what is the tendency to rotate in anti-clockwise? This is what we want. Then it is df2 by dx minus df1 by dy. What is if I have a vector field capital F? Now consider this is rectangle. This is rectangle. The boundary of this is rectangle. What is tendency of this is vector field? What is tendency of this vector field to rotate this rectangle in counterclockwise? That is df2 by dx minus df1 by dy. This df2 by dx minus df1 by dy is called curl. That is tendency of the vector field capital F to rotate something. This is called curl. We will see this is also called circulation density. Circulation density. Now let's not talk about the curl df2 by dx minus df1 by dy. Okay, if f1 vector is not changing if we go along y-axis, then df1 by dy is 0. If f2 vector is not changing if I go along x-axis, df2 by dx is 0. If that is the case, then there is no curling. Means df2 by dx is 0. df1 by dy is 0. 0 minus 0, 0. It won't rotate. Okay. But if there is df1 by dy is there, df2 by dx is there, if both are same, if both are equal, then df2 by dx minus df1 by dy equal to 0. Means df2 by dx equal to df1 by dy. If that is the case, again it will not rotate. df2 by dx and df1 by dy, if they are 0 separately, it will not rotate. If df2 by dx is there and df1 by dy is there, and if they are same, again it will not rotate. So we have, okay, this is two conditions. Third condition is, if I can calculate line integral from point A to A along any path, along any boundary. Now we are entering into surface. Can you see boundary? I am changing my name from path to boundary, from path to boundary. So from the line integral to boundary. So if to surface, if I have a surface like this, if I have a surface like this, then this is the boundary. Can you see? This is the boundary of the surface. As good as I had taken a line rectangle. So this is a line rectangle along the boundary of the surface. Now if I calculate line integral along the boundary of the surface from point A to A, that is A to B, B to C, C to D, D to A. If this line integral is 0, again it will not produce any rotation. There are three things that we are getting when vector field will not produce rotation. One is df2 by dx is 0 and df1 by dy is 0. It will not produce any rotation. Or if df2 by dx equal to df1 by dy, then again it will not produce the rotation. Or if I calculate line integral in a closed loop, means A to A, that is A to B, B to C, C to D, D to A. Or in a closed loop, in a sense, we can take rectangle also. If that is the case, then from here back to here, from here back to here, if I calculate line integral, means piecewise I make this circle piecewise. Rectangle I make 4 pieces. Circle also I take many pieces and calculate the line integrals for separately. And if I add it and it point A to A in a circulation, if it comes as 0, again it won't produce any rotation. It won't produce any curling. Okay, so three way we have learned, it will not produce any curling. But problem with the line integral is, if I am calculating line integral of a rectangle from here to here, from here to here, here to here, here to here, here to here, and this line integral is 0, then there is no problem. But if this line integral is not 0, then it depends upon how big the line I have taken. If I have taken this line this big, and then this distance what I am taking, if this distance is very high, and then line integral will keep changing, because line length we are changing, and then the way we talk like x plus yi. If y is more, then the difference, then net line integral that is not 0, it will change. So line integral is dependent upon the area of the rectangle that is under this rectangular region. If this is rectangular region, and whatever the area is, net line integral will change if I make it bigger, 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 bigger. Makes sense, right? If consider from here to here, I have a line integral. From here to here, I have a line integral. But in line integral, we have y factor. If y factor is growing, then this line integral is bigger. So if y factor is growing, the line integral is bigger. Similarly, if I have line integral with for f2 component also, if this side is growing, then line integral is changing. So as we grow in the area, the line integral is changing. If it is same as, consider this is iron. Consider this is iron. It is not iron, but consider this is iron. What is the weight of this iron? The weight of this iron is 50 gram. Consider 50 gram. But if I make it bigger, 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 it will probably become 100 kg. If it is 100 kg, I don't know what is the density of this item. This is how Archimedes worked. If anyone remembers Archimedes, and then he did eureka, right? Means he found that there is a kind of something, I believe, that mukut that king wear, and the kind of the big metal cap the king they wear, and that the job was to find out without breaking it that how much the metal turban, you can say, how much is gold, how much is silver, how much is diamond, whatever, what how much the it is it how much is the kind of because someone made it and he mixed. I think it was supposed to be made from the gold only, but someone mixed silver and other metal, nickel or whatever, and now king is feeling that it is not pure gold. Then if it is not pure gold, then how much other metals? Then when you sink in the water, then it will feel lighter. How much it is lighter? It depends upon the density of the material. So main thing is density of the material. If I know the density of this material, then I can estimate this material is made up of what? Iron has different density, gold has different density, silver has different density, and like that. So if that is the case, then what is the, if I calculate line integral along this rectangle for a particular vector field, then line integral is different. If I calculate for bigger rectangle, then line integral is different even though the vector field is same. What is tendency of this vector field to rotate something? I cannot estimate through line integral, because the way I am growing the line integral, the net line integral is changing. If it is 0, line integral is 0 all along, then immediately I can say that it will not rotate. The vector field had tendency not to rotate. But if it is not 0, then depending on the size of the area, line integral will change. Now if I want to know the tendency of this vector field to rotate, then I have to calculate the line integral of any line integral of a circle. So line integral of this circle, because line integral is nothing but force or vector field multiplied by the line distance. If it is small, the line integral will be small. If it is big, line integral will be big. If it is bigger, then line integral will be bigger. If that is the case, then what is tendency of this force to make something rotate? If that is the case, then it is line integral whatever we have calculated divided by the area. So if line integral is small, if line integral is smaller with a smaller area, then dividing it by area, it will give some value. If I increase it and line integral is more, then dividing by bigger area will give same thing. That is called vector field density or circulation density. Line integral is sometimes defined as circulation, because if I take a skeleton, then it looks like a line. If I take a surface, then it looks like a kind of a circulation. So what is circulation density? Circulation density is whatever line integral I am calculating in a closed loop, point A to A, whatever it comes divided by the area. So if area is big, line integration will be big, divided by the area, it will come to same situation. If area is small, then line integration will be small, divided by small, it will come to same thing. What is the same thing? Circulation density is line integral in a closed loop, closed path from same point to same point, that is closed path. Line integration in a closed path divided by whatever the closed path generates an area, divided by that area, that is circulation density. Circulation density is tendency of any vector field to rotate something. Then df2 by dx minus df1 by dy, that is the curl, that is also a tendency to rotate something. If both are same, both come a tendency, because the line integral, that is capital F dot dr vector from point A to A divided by the area that closed loop is making, this is constant. If vector field F is constant, this is always constant. If you grow in the line, then line integral is bigger than divided by area. Area is bigger. If area is very small, the line integral is also very small. Small by small, same thing. It is a constant. If that is the case and it is not zero, it has curling tendency, then it is considered that line integral by area is the curling tendency. Whereas we saw the curling tendency is df2 by dx minus df1 by dy. So this is called the okay. So this is called geometry. This is called geometric way to calculate the curling, whereas this is called algebraic way or Cartesian way to calculate the curling. line integral integration from a to a or in a closed loop capital F dot dr vector divided by the area. What closed loop makes an area divided by that area. If this is the curling factor, this is the way we calculate we call it calculating the curling factor through geometry. But df2 by dx minus df1 by dy, it is called calculating the curling through Cartesian coordinate or through algebra. So this is two way we can calculate the circulation density. Both are same as per the Green's theorem. Green's theorem say that in a closed loop, the line integral is nothing but the closed loop make a surface, right? Then surface integral of curl df2 by dx minus df1 by dy with dA. When we integrate with the surface area, dA is the xy plane. If I have a surface, if this makes a surface, then integral of this surface, integration S, capital S, integration of the surface, integration in a closed loop, capital C, capital S, integration over the surface of the df2 by dx minus df1 by dy, dx dy means xy plane. If I calculate integral over surface of df2 by dx minus df1 by dy, it will bring algebraic equation, right? df2 by dx minus df1 by dy, it will bring an algebraic equation. This algebraic equation integration over a surface with the xy plane will give you same thing as per the Green's theorem. What you calculate the line integral of capital vector f1 along this surface. If it is surface, then along the boundary or along the circulation. So circulation, if this is circulation, that is integration, that is closed loop integration capital F dot dr vector, if that is equal to as per Green's theorem, then integration on the surface df2 by dx minus df1 by dy and d area dA. If I take out dA this side, then both are same. Means circulation density by dA, where area is very small, that is dA. Circulation density of an area that is very small equal to df2 by dx minus df1 by dy. Okay, we will prove more on it, but this is what it is. So if I calculate line integral or circulation, that is integration in a closed loop capital F vector dot dr vector divided by whatever this closed loop is making the area, divided by the area. If area is very small, then it becomes delta A or dA. That is equal to df2 by dx minus df1 by dy. If I take on this side, then it becomes Green's theorem. Otherwise, this is the equation of curling and circulation density. So circulation density is nothing but curling only, but curl has direction. df2 by dx minus df1 by dy will have a direction. Okay, that will, if our surface is on xy plane, then df2 by dx minus df1 by dy, the direction will be along z axis. It is nothing, it looks like a thumb rule, right? Right hand. If this is the rotation direction of, so surface has a direction now, because this curl is a direction, right? This line has a direction counterclockwise. So if it is counterclockwise, then the net curling has a direction. The net curling is along z direction if it is counterclockwise on xy plane. If that is the case, then how we can df2 by dx minus df1 by dy, quickly I can calculate. df2 by dx minus df1 by dy, quickly I can calculate, and whatever is coming, if capital df2, if f2 is in y direction and f1 is in x direction, then net is in z direction. We are getting a smell of cross product of two vectors. If that is the case, then if f1 and f2 are in xy plane, the net curling is in z direction. But if it has three components, f1, f2, f3, f1, f2, f3, if that is the case, then this surface can it is not required that it will be on xy plane. It can be anywhere. But if that is the case, then this curling equation will change. Now, rather than only df2 by dx minus df1 by dy, it will have df3 by dx and df3 by dy component also. That we will see. In that case, if I calculate the curling through Cartesian product, then the curl direction will be perpendicular to the surface. But what about calculating through circulation density, the curling factor? Curling factor through circulation density, also called through geometric way, then it is line integral along this line of any vector field f, whatever I calculate divided by the area. It is coming as pure numeric static. It is not vector. What about the vector? Vector is, if I take a surface, then vector is perpendicular to it. But how I know what is the vector? I can take surface any along, right? Here I can calculate circulation density against a vector field. I can calculate circulation density against same vector field. I can calculate circulation density against same vector field. If I keep changing this, wherever I am changing, the circulation density direction is perpendicular to the surface. Perpendicular to the surface. Perpendicular to the surface. If I keep changing it, and in one direction I found that net line integral is maximum, that is the that area. This here this is vector field. It is on xy plane. Now I am calculating the line integral. It has some value. Now like this, it has different value. The r vector is changing. Capital F is same. A to A, but r vector is changing. Line integral is different. Line integral is different. Line integral is different. If I keep changing, making the same shape, and there will be some moment will come where line integral will be maximum. At that moment, whatever the perpendicular I am seeing through the surface, that is the direction of the curling. Okay, and what is the magnitude of the curling? That is the line integral I am getting divided by the area. Okay, so that is circulation density. Circulation density is nothing but line integral divided by the area. Area is constant. Vector field is constant. A to A means everything is constant. While keep changing in r vector. Keep changing the r vector so that line integral will be maximum. If that is the case, then whatever the circulation density I am calculating, line integral divided by the area, that is the net curl, and direction of this perpendicular surface is the direction of the circulation density. So circulation density is nothing but curl only, but it should be maximum. Okay, if you don't want to go through maximizing it so many times here and there and then find the maximum line integral and then calculate it divided by the area, that will give you the curling factor or circulation density, and then you decide for the direction of the circulation density, then go for df2 by dx minus df1 by dy, or go in the 3D. 3D, what is the circulation density is a matrix. You have to keep a matrix, and I, j, k, and then d by dx, d by dy, d by dz, and f1, f2, f3. Now, if you calculate the determinant of this, where I, j, k, d by dx, d by dy, d by dz, f1, f2, f3. Now, first column and first row, calculate the determinant, and it will be in I direction. Now, second column and first row, if you close, then the determinant what you make, it is in j direction, k direction. Whatever the net is coming, that is the direction of the curve, and this is how it will be. So this is, we learned that circulation line integral divided by area, that is circulation density. Circulation density is nothing but curl. That is the tendency of any vector to rotate something. We will bring more interesting thing here, and we will proceed curl. This is commercial calculus. So we will see it. Meanwhile, if you are capable, then feel free to support us. Our telephone number is 91, that is India, 94831 60610. 91 plus 91, and number is 94831 60 610.